Welcome to the 6th lecture on computational commutative algebra. So in this lecture, we will look at what is called initial terms and initial ideals. And after having put all these things together, we will prove the version of Hilbert basis theorem that we are after. So recall that we are working over a polynomial ring over a field in finitely many variables. And we now R is given a monomial order could be lex, could be graded lex or something completely different. Okay. So it has a monomial order. Now definition. Let f be a non-zero polynomial. A term of f is a monomial of R that appears in F with a non-zero coefficient from K. Okay. What exactly we want to emphasize with that? For example, y square is a term of x plus 5y square. Let's say this is a polynomial in Qxy. I mean, if you in characteristic 5, this coefficient is 0, so one has to, it's just 2. Okay. So that's a non-zero coefficient in characteristics different from 5. So here we chose a field of characteristic 0. Okay. So this is a term of it, but not of x plus xy squared. So what multiplies y square should be an element of the field and not another variable or another polynomial, or of x square plus y cube. Okay. So I hope you understand what is meant by a term. So it's a monomial that appears with a non-zero coefficient. Now we can define an initial term. Let f be a non-zero polynomial. Okay. The initial term of f is the largest term of f with respect to the given monomial ordering. Okay. It is denoted, so this is the, so it is denoted by in f. Okay. It's also sometimes called, so let me just write here, or maybe okay, sometimes called leading term Now let's look at, so here are three polynomials. This is again the same polynomial ring in three variables, x, y and z. Order is graded lex. So here f1, there are three terms, x squared y, x y squared and y squared. So if you compare these two are degree 3 polynomials. This is a quadratic polynomial, so it's the leading term is going to be one of these things. Here is x squared y and this is xy squared, and in lex, so they are the same degree, so we just use lex to compare, we would just get x squared. Here in f2 there's an xy which is degree 2, there's a z, so this is the one that is that's bigger in glex, so xy, and here both of them have the same degree, y squared and xz, so we just have to use lex between them. This one involves x, this does not involve x, so if you write out the lex comparison for these two, one would see immediately that this is the leading term. So so the Macaulay command for finding the leading term is lead term with a capital T. So one thing to keep in mind is that when you ask Macaulay for a leading term, it will also put the coefficient. Typically when we discuss the problem, we will assume without loss of generality that the coefficients are 1. Okay? So one has to just keep that in mind when that sometimes Macaulay is, what is convenient for us to discuss is probably not what is convenient to be programmed. So that one has to worry about. Okay? So this is an example. Okay. So now let's extend this notion to ideals. Definition. Let I be an R ideal. Okay. The initial ideal of I, again all of this is with respect to the given order, monomial order with respect to, is the ideal generated by the initial terms of the non-zero polynomials in I. Okay, so this is not this set itself is just a set of monomials. It's not an ideal. So we look at the ideal in R generated by this set, and it is denoted by in I. And few remarks. One, initial ideal of an ideal is a monomial ideal because it is generated by the initial terms. And two, because it is a monomial ideal, it is also finitely generated. This is what we proved in the previous lecture. Okay? So this is a finitely generated ideal. And now let's look at, let's compute this in Macaulay, and we will see some small surprise. So here we ask, so the command for the computing initial ideal is also lead term. So if you give lead term, it will check its argument and decide what is to be computed. So we ask lead term of ideal generated by f1, f2 and f3. Recall f1, f2, f3 are these, and their lead terms are x square y, xy and xz, coefficient time -1 times xz. So if you look at the ideal generated by them and ask for its initial ideal, then suddenly we see that there are more than 3 things here, because there was an x square y and xz and a yz. X square y, xy and xz. But now we see, okay, there is an xy, but there is no x squared y, and then there is an xz, but then there are 3 other things which are new, which we did not know. So let's try to understand what happened. Okay, there are 2 issues to be understood. One, x squared y is not in this list, and then in addition there are 3 other things. Okay, let's understand these things one at a time. Okay, x squared y, it's not there because xy is there. X squared y is a multiple of xy, so any ideal which requires x squared y is already taken care of by this xy. So that explains why x squared y is not there in this list. Okay, so now let's try to understand some of these things. I mean, we will not explain all 3 of them, but it's the same reasoning. So let's do this computation. Okay, so if we took f1 minus x times f2, so this is because, how did we make this decision? The leading term of f1 was x squared y and leading term of f2 was xy. So I multiply by x so that the leading, and then take the difference, so that the leading terms cancel each other. Okay, that's what we did. Okay, so we get some polynomial whose leading term is xy squared, which is divisible by the leading term of f2, and okay, so which you need to multiply by a y. Okay, so we take this. So the word OO refers to just the previous output. OO minus y times f2 will now cancel this term also, and we have some we get some new expression. Okay, now this one's leading term is xz, and we know that in the last polynomial f3 there was a minus xz, so we add these 2 together and we get 2y squared plus yz. Now the leading term of 2y squared is y squared, but because Macaulay has to keep track of when you write programs, we cannot lose these coefficients. So here in the algorithm that Macaulay was running, it would give 4y squared, but the point is the same. There is a polynomial in this ideal whose leading term is y squared, which is not visible just by looking at the generators itself. Okay, so that is how this term came. This 4y squared came. Okay, and similarly, one can work more and see where the z cube came in and the yz came in. Okay, so this is what is meant by initial ideal, and what issues one has to worry about going about computing them. Okay, so with this, we have now learned a way to convert an arbitrary ideal to an initial ideal, to a monomial ideal, and now we want to use this idea to prove Hilbert basis theorem. Okay, so recall Hilbert basis theorem. Okay, so for fields, okay, the point that we want to prove is K field are a polynomial ring in finitely many variables. So that's then R is Noetherian. Okay. This is what we will now prove. Okay, so prove. Okay. Let I be an ideal. Okay. We may as well assume that I is a non-zero ideal, because if it is 0, it's always finitely generated. Okay. And we define J to be the initial ideal of I, of R, where this is any monomial order. It doesn't matter for this proof what that is. Okay, so now, so J is finitely generated. That was the, we know that we've seen that all monomial ideals are finitely generated as a consequence of Dixon's lemma. Okay, so so J is generated by initial terms. So therefore, there exist G1 through Gm inside I such that J is generated by the initial term of G1 up to initial term of Jm. Okay. Well, a generating set for J is the initial terms, and then there's a by Dixon's lemma there's a finite set, and okay, so they are initial terms of some elements from I. Call those elements of I G1 through Gm. Okay, so J is this, and so our claim. So we want to show that J is generated by the initial terms of these, then I is generated by those elements themselves. Okay. This need not be a minimal generating set, which you will see some examples in the exercises, but it is generated by the same set whose initial terms generate the initial ideal. Okay. So we'll prove it somewhat informally. The reason is I would like you to understand what is going on in the argument rather than writing it out formally in some setup. Okay. So let F be inside I non-zero. If it is 0, then it is already in the ideal generated by the G's. Okay. So recall that I contains the ideal generated by the G's. What we want to show is the other containment. If F is 0, then it's already here. So we take a non-zero element, we take an element here that's non-zero, then prove that it is there. Okay. Since F, the initial term of F is inside J, there exists a J1, index J1, such that the initial term of J1 divides the initial term of F. Okay. So this is a property about monomial ideals and monomial elements of monomial ideals, okay, which is that if you have a monomial ideal and a monomial, then a monomial of R is inside the ideal if and only if it's divisible by one of the generators. Okay. So again, you can do this as an exercise. I will write this up, and one uses this. Okay, so this is divisible by that. Okay, so what does that mean? What does that mean? There exists a monomial mu1 in R such that the initial term of F is mu1 times the initial term of Gj1. Okay, that's just divide, so the quotient, when you divide you get another monomial. Okay, so now we are going to proceed by induction. Okay. Let's define F1 to be F itself. So we're going to construct a sequence of polynomials. We define F2 to be F1 minus mu1 times Gj1. So let me just restate what we did. We found J1 such that initial term of Gj1 divides initial term of F1, and mu1 is the quotient that you have to multiply to get them equality. So we just subtracted that from F1 to F1 minus mu J1. What is the property of this? If F2 is not 0, then we can talk about the initial term of F2. Okay, this has to be less than the initial term of f1. Because the initial term of, this was multiplied precisely to cancel the initial term here. So let me be vague here. Need to take care of coefficients. So when you say initial term, we are saying we're taking it with a coefficient 1, but that may not work all the time. So maybe I should just put this here. Use appropriate coefficient from use appropriate coefficient from K here, and what is here? Here is here. Okay, it may not be just subtract, it may not be -1, but if you appropriately multiply by a coefficient, you can get this result. Okay, you can cancel the initial term. That's what one has to do. Okay, so we get this, and okay, so if you want to show f1, so then if f2 is inside, okay, f2 is inside the ideal generated by the G's, will now imply that f, which is f1, is also in the ideal generated by the G's. Okay, so note, okay, this would imply that. So hence, it's enough to prove for f2 that f2 is inside the ideal generated by the G's. Okay, so if f, otherwise just continue. So repeat the same procedure up to f2. Okay, we would get an f3, which is some f2 minus some mu2 g j2. These values don't really matter. All that matter is such that, so again one has to find appropriate coefficient here, not just -1, the same discussion that we had to. If f3 is non-zero, then in f3 is, this is initial with respect, there's only one order in question, is strictly less than in f2. Okay, so this way we can get f1 like this, such that so assuming that this continues forever, we would get fi plus 1 such that initially this is less than in fi. Remember, this question about initial ideal comes in only if the new polynomial that we just constructed is non-zero. So so f1, f2. Okay. So remember, this is a descending sequence of monomials. In f1 is the largest, then is in f2, then is in f3, and so on. Okay? Yeah, we just have to prove that. So let's, and we can stop, I mean, this construction can stop as soon as we hit an fi which is inside G. So note that the construction of the sequence fj can stop as soon as there exists some I such that fi is inside the ideal generated by the G's, because then, as we explained how to go from f2 to f1, we can go backwards and prove that f is inside I, f is generated by these things. Okay, so let's continue like this. So we want to show that if this doesn't happen, then we will get, okay, so we want to show that there exists some I such that fi, if you keep constructing like this, we would end up with an I such that G1 through Gm, this is inside G1 through Gm. Okay, so this is what we want to prove. Okay. So if this doesn't happen, then fi is non-zero. So by way of contradiction, assume this does not happen. Okay. So this is the assumption that each time one constructs this thing, one gets a polynomial which is not in the ideal generated by the G's. Okay, let's understand that. So then this, first of all, then all the fi's have to be non-zero, because any zero polynomial is already in the ideal generated by the G's. So fi's are non-zero, and we get a descending sequence of monomials in F1. In is always with respect to the given order. There's only one order in question now. Like this. Descending in the sense that with respect to the given monomial order, this is descending. Okay. Strictly descending. Okay. So then what we want to prove is the following. So claim such, infinite. So this is infinite. That's the point. Okay. So there does not exist any infinite descending chain of monomials. Again, descending chain means with respect to the given monomial order. Okay. So how do we prove this? So let lambda be some monomials nu1, nu2, such that nu1 is bigger than nu2, bigger than, and so on. Okay. Now by Dixon's lemma, this has a finite set of minimal elements. So let's call them I1 through IR. There exist I1 less than I2 less than IR such that this new I1, new I2, new I3, new I3 up to new IR is the set of minimal elements of lambda by divisibility. So in this sentence we are using order and divisibility simultaneously. Minimal here means by divisibility. Okay. So what does that mean? Okay. Therefore, for all I greater than IR, nu I is divisible by nu j sub k, nu I sub k for some k in the minimal elements are nu sub I1 up to nu sub IR. One of these things is going to divide that. Now let's think about this. This is a monomial that divides that. Okay. So note that nu I is less than nu ik. Ik comes before I. This way is bigger than nu I. This is by hypothesis. Okay, and this divides that. So let mu be nu I divided by nu ik. So this is a monomial. Okay, so this is with respect to the given order, and mu is a monomial. Okay. Therefore, mu is bigger than 1. This is the definition of a monomial order. Now let's look at, put these two together. Mu is bigger than 1. Now, if you multiply both sides by nu ik, mu times nu ik, which is nu I, is going to be bigger than nu ik, but hypothesis was the opposite, that nu ik is bigger than nu I. Okay, this is a contradiction. Okay, and where did we get this contradiction? We got this contradiction by assuming this. We got this contradiction by assuming that this does not happen. For every I, fi is not inside. So this was the assumption. This assumption, and when we proceeded with this assumption, we got an infinite descending chain of monomials, and then we put that's not possible. So the contradiction is in the assumption. Therefore, there exists I such that fi is inside G1 through Gm, and then we saw that this implies that fi minus 1 is inside G1 through Gm, and proceeding like this, f, which is f1, is inside G1 through Gm, and this implies that I is the ideal generated by G. Okay. So this is the proof of Hilbert basis theorem that we do using this idea of monomial orders, initial ideal, etc. Okay. So this is the end of this lecture.